Yeah.
Okay. This tutorial, we talked about density of states, and you arrived to the last tutorial, right?
Yeah, you give me 2 examples, right?
Okay, yeah. Okay, so because now we are going to talk on something that is based on the density of states. We need to use it here. Okay, so we're talking on the bimodel. Okay, so I think in the lecture you didn't reach to the final data of the bimodel, right? You started to talk about the bimodel?
Yeah, this morning.
Okay, yeah. So tomorrow you will finish the Dubai model. So something I will say here, just take them as, I don't know, as general law, and tomorrow you'll see why they are true. Okay, so in a nutshell, so the Dubai model, right, is a model that deals with a lattice. Okay, so if I have a lattice of atoms, okay, and each atom can move in the lattice, okay, a little bit from its equilibrium position. Okay, so it can move in the lattice, and so the model says that, okay, instead of looking at each atom, okay, so that the motion of the atoms is complicated, okay, instead of looking on each atom, let's look at the whole lattice and say, okay, let's look at waves in the lattice. Okay, so this is called phonons. So each phonon is a vibrational mode in the lattice, meaning every atom in the lattice vibrates in the same frequency. Okay, one wave in the same frequency in the lattice.
Yeah.
Okay, so for example, yeah, if I have, let's look at one-dimensional lattice because it's easy. So one vibrational mode can be this atom goes to here, and this is here, and this goes to here. Okay, so each pair of atoms do get close and then catch distance, and then get close and then catch distance. Okay, and the motion occurs in the same frequency. Okay, so these phonons, these vibrational modes, can describe every motion in the lattice. Okay, so we're talking on phonons, and then each phonon has a frequency. Let's say some frequency omega I, okay? And then we can look at the lattice as an ensemble, as canonical ensemble, and say, okay, let's write its partition function. Okay, because the modes now does not depend on each other. Okay, each mode
each model.
Has its own energy.
You mean two photons?
Yes.
And each two is dependent.
Yes, exactly. So I can describe the lattice with the subsystem partition function. Okay, because the energy of each phonon depends only on its frequency. Okay, it doesn't interact with other phonons. Okay, so the partition function, the length of the partition function, equals to ln of subsystem partition function for each phonon, and we're summing on the possible frequencies. Okay, we're summing on every partition function for each frequency of phonon. Okay, this is the theoretical background I'm giving here. So now just a few equations that you'll see in the lecture tomorrow or next week. Okay, so just take them as correct for now, and you'll see why in the lecture. So the density of states, okay, I forget to write here the density of states in the integral. Okay, so this density of states for the bimodel is given by 3v omega squared divided by 2 pi squared vs in the third. Okay, so the assumption of the bimodel to get this density of states.
What is V?
What?
What is V?
Okay, so yeah. So the assumption of the bimodel, it's from the assumption for the bimodel that says, okay, now that we split the lattice to phonons, okay, now that the bimodel does its assumption and say, okay, let's assume that we have a linear dispersion in the model. Let's do something like this. Okay, let's just first write the assumption of the bimodel. So it assumes a linear dispersion in the lattice such that omega equals to Vsk, where this Vs is the speed of sound in the lattice. Okay, so it assumes a linear dispersion between this omega to this k. Okay, and under this assumption, the density of states is given by what I copied previously. So we have 3v omega squared divided by 2 pi this Vs in the third. Okay, so two things here. One, this is true, okay, for frequencies that are smaller from what we call the dBi frequency. Okay, and above this frequency, we say we don't have any possible states. Why is that? Because we work in a lattice. Okay, so the waves we can create in the lattice, okay, depends on the structure of the lattice. Okay, if I will back to this this drawing. So just think that if we want a wave with some frequency, yeah. So let's say, okay, let's say we have a wave. Okay, so in order to describe it with a finite number of atoms, okay, so let's say we want a frequency like this, but we have atoms only in the peaks of the wave. Okay, we need at least several more atoms in distance of half of the wavelength in order to get this wavelength to be described properly. Okay, because otherwise all the atoms just go up and go down together, and we actually have no wave in the lattice. Okay, just all the lattice goes up and goes down.
Yeah.
Okay, so we have particles between those peaks to get to describe properly the wave. So we have some maximal frequency we can get because we have finite number of atoms. Okay, and distance between the atoms.
Oh, yeah. So why omega can change?
What?
You say omega equals to Vsk, and Vs and k is constant. Why it can change?
Yeah, okay, so this is the assumption of the bimodal of some dispersion, dispersion relation. Okay, between the frequency and the wave number.
Oh.
Okay, we can have any other dispersion relation. Okay, so this is the specific relation for the bimodal that gives us this density of states. Okay, we can have other relation that gives us different density of states, but still if we work in a lattice, we have this condition. Okay, this condition is not from the assumption of the bimodal, but this is due to the structure of the lattice. This just has to be true. Okay? For a lattice. Okay, so this is the only assumption we did so far. Okay, and so this is the first thing in this density of states, and the second thing is this 3 here. So if we had calculated the density of states as we did last week for this dispersion relation, okay, we would get this term but without the 3. Okay, so this 3 is generation, degeneracy in possible waves in the lattice. Okay, so in 3-dimensional lattice, we have 3 degeneracy of waves. So we have 1 possible for longitudinal wave. Okay.
Long wave?
What?
What do you mean, long wave?
So we have 2 kinds of waves, right? We have like sound waves that are longitudinal, right? That the atoms moves in the same direction of the wave.
Yeah.
Okay, and we have transverse waves. 2 modes of transverse wave. This is 1, and this is 2 modes. That the atoms move in perpendicular to the wave.
Yeah, I know.
Okay, wait. So this is this 3 degeneracy. Okay, because we have 2 modes here and 1 mode here. So in total we have 3 possible modes for each frequency. Okay, so we have the degeneracy of 3. Okay, so we have 2 possible directions, one up and one in 90 degrees.
Oh, you mean this?
Yes.
So this is 3 because in 3 dimension.
Yes.
Okay.
Yes.
Okay.
Okay. Ready?
Yeah.
Great. So where were we? Okay, we talked about density of states. Oh, right. So now the question is how we find this the bifrequency, this critical frequency. So we're saying that when we're summing up on all possible states, okay, for all possible frequencies from 0 to this critical frequency, we expect to get the whole number of possible modes. Okay, where n is number of atoms in the lattice. Okay, so if we're applying the density of states under the assumption of the bimodel, this assumption, we're getting that this critical frequency, this Debye frequency, equals to Vs times 6 pi squared n divided by 3 in the power of 1, 2, 3. Okay, and last thing, last formula. You'll see it in the lecture that we can calculate the density of states. Okay, if we have the dispersion relation between omega and k, okay, we can calculate this density of states is V divided by 2 pi squared k squared that dependent on omega, okay, dependence on omega, times the derivative of k relative to omega. Okay, now let's do a quick question. Can I raise it?
Yeah.
Okay. Okay, so we have a lattice. We have n atoms. And dispersion relation so we have omega equals to ck in the power of 3 divided by 2. Okay, so C is constant, and this size of the lattice is L by L by L. Okay, so we have the lattice, okay, but pay attention that this dispersion relation is not according to the Debye assumption. Okay, so we use the same technique, but with different dispersion relation. So first we want to find the density of states. Okay, so here, because we have the dispersion relation, we have easier work from what we did in the past tutorial. Okay, because we know, right, the formula I wrote here, right, we know that we can find the dispersion, the density of states with, let's write it again, so we can find it with V divided by 2 pi squared k squared times the derivative of k relative to omega. Okay, so all we have to do is to extract k from here, okay, and just insert it to this formula. Okay, so it's not a hard job. Okay, so we can take k to be omega divided by c in the power of 2 on 3. Okay, and then, okay, we can get the derivative, we can insert the k squared, and we will receive that this density of states is final answer. So we have L in the third, omega divided by pi squared, c squared. Okay, so we have the density of states. Okay, so now we want to find the Debye frequency, okay, the maximum frequency we have in the lattice. Okay, so in order to find the omega d, right, we said we need to use this integral on the density of states from 0 to the Debye frequency, and this should be equal to 3n. Okay, so we need to insert this density of states to the integral to solve the integral, and then we will have an equation that we'll need to extract this omega d. Okay, so because we missing a little bit time, let's just write the final answer because it's just solving this integral. Okay, so the final answer is that omega d equals to 6n pi squared c squared divided by m to the third. Okay, so we have the dependency of omega d with this n, okay, with the number of atoms. Okay. Okay, so we can see from this answer that as we will increase the number of atoms in the lattice, so the maximal frequency will be increased. Okay, because we will be able to make more waves in the lattice. Okay, because the atoms will be closer. Okay, and the final section for this question. We want to find heat capacity as function of the temperature. Okay, so this is a bit more complicated. Okay, so first, in order to find the heat capacity, we need to find the internal energy of the system. Okay, because, right, the heat capacity is the derivative of U relative to the temperature. Okay, so we need to find this internal energy. And the internal energy of a system, okay, so we said that we deals with a lattice after we break it to phonons as an example. Okay, so we need to extract the internal energy from the partition function. Okay, so the partition function, or let's write it like this. So let's start with the internal energy. Okay, the internal energy in the canonical ensemble is derivative according to beta of ln of the partition function. Okay, so let's write it in a more ordered way. Okay, so we write in the start of the tutorial that the ln of the partition function equals to we write it as integral of ln z omega d omega. Right? We said this is the ln of the partition function. Okay, so let's insert it under the derivative, and we get that the internal energy equals to minus derivative relative to beta integral, and we're summing up on all possible frequencies, okay, meaning from 0 to the divide frequency. Okay, and let's insert this ln z omega d omega. Okay, and this is the subsystem partition function for one phonon. Okay, so let's see what is subsystem partition function. Okay, so z omega equals to summation on E minus beta times the energy, right? The general partition function. And then the energy of the phonon is an energy of a wave. Okay, so we have here the energy to be h bar times the frequency, right? And we're adding here a multiplication by Ni. That means how many phonons we have in the system with this frequency. Okay? Yeah. Okay, and then we're summing up on the possible number of phonons we have in this frequency. Okay, we're summing up on Ni. Okay, so we can have 0 phonons with this frequency, we can have 1 phonons, and we can have infinity phonons with this frequency. Okay, so we're summing from 0 to infinity. And this equals to, you'll see it in the lecture, 1 over 1 minus E minus beta h bar omega. Great. So let's insert it to the integral. And what we get So we have here the internal energy equals to minus derivative relative to beta of integral from 0 to omega d ln of this subsystem partition function times the density of states. So the density of states we have L to the third times omega divided by pi squared c squared d omega. Okay, and so we don't know how to solve this integral. Okay, so what we're doing is first we do the derivative. Okay, we insert the derivative under the integral. Okay, and first we do the derivative and then the integral. Okay, so we get, if we do this derivative according to beta, we get that this internal energy equals to all the constants. So we have L in the third times h bar divided by pi squared c squared, and we have this integral of omega squared divided by e beta h bar omega minus 1 d omega okay, and then in order to calculate the heat capacity, we do the same, but now we do derivative relative to T and not to beta. Okay, so this will be the derivative of fuel relative to T, and then we get the heat capacity with some integral. Okay, but we get the heat capacity. Okay, so we need to stop here because they are already have another class here. Okay, we didn't do everything I wanted. We have another part on black body radiation that we didn't do. So there are the tutorial pages in the Moodle. Okay, just read the final part on the black body radiation.
Okay.
Okay. Yeah. Sorry about that.
Yeah. Thank you.
You're welcome.